Hello, everyone, and welcome to the Mindscape podcast. I'm your host, Sean Carroll. The big news in Mindscape land, as you may have heard, is that I've opened a Patreon account. That is, in other words, a way that you can send me money for me making podcasts. This is something I've been thinking about for a while. As much as I love the podcasting, and I do love it, and I wouldn't do it if I didn't enjoy it, and in many ways, it's an excuse for me to talk to interesting people about topics that I wouldn't ordinarily get to think about. It also takes time, and it even takes money and so forth. So being recompensed in some way is a good thing. Even though the podcast is relatively young, I've already gotten a few emails from different people, different companies who are interested in placing ads on the podcast. This is the traditional way that people can support their podcasting efforts. The host will read an ad in the beginning or in the middle and talk about how wonderful this particular smoothie is, or that particular penknife, or whatever it is that is being sold at the time. I don't really have moral objections to that. It's, how commerce works. I wouldn't advertise something that I didn't like. I would actually be very careful about what it was that was being advertised. But I do have some aesthetic worries. I just like it better when the podcast is nothing but the substance of what we're talking about and not being interrupted by ads. So the idea behind the Patreon is to replace the revenue that would come in from ads with just people giving money in exchange for receiving the podcast. So you can go to Patreon, that's patreon.com/Sean M. Carroll, or you can just go to the Mindscape podcast homepage, preposterousuniverse.com/podcast, and there's links there to the Patreon page, and then you can pledge. So what that means is you agree to give $1 or $2 or $5 or $10 or whatever amount of money you want to pledge. That will be for every individual episode. So sometimes it's done per month or per time period. I can't absolutely promise that the rate of podcast is going to be exactly the same every month. So I think that it's more fair to charge per podcast. So $1 per podcast, it's not that much. It would be ideal in my world if I could just charge everybody 10 cents per episode of the podcast, everyone who listened. I would probably be making a lot more money than I would with ads or Patreon or anything else. But there's no such system, as far as I know, to make that work. Maybe someday cryptocurrencies will let that happen. You'll be paying me in Bitcoin or something like that. So let's see how this goes. If I can make anywhere close to the income from Patreon that I would from ads, then I prefer to just stick with that and never have ads. But, no promises. We're trying things. I'm learning. I'm new at this. So, let me know what you think about it. And please, if you like the podcast, do think about going and pledging. I completely understand if you don't. I'm sure that many listeners, have lower incomes than I do. It's completely okay if you don't want to pledge. It's a bit of a hassle in a lot of people's minds to, go sign up, put in your PayPal, your credit card or whatever. So I'm not guilting anyone into doing this. This is completely optional, completely voluntary. It's nice. It makes me feel good and it makes you feel good. It's a way to give back to the podcast if you're enjoying it. So I very much appreciate if you do that. I certainly appreciate those of you who have already signed up. Thank you very much. It makes me feel like I'm doing something good and makes me motivated to do more of it. There's also a slightly more tangible benefit involved in that I'm going to try to do monthly or maybe once every 2 months an Ask Me Anything, an AMA, where subscribers can ask questions, Patreons in other words, people who've pledged something, and I will answer them in the form of a podcast, and it will be available exclusively to the supporters. So for your $1 an episode or $2 an episode or whatever, you get to listen to me answer some questions about something. In fact, if you go to the Patreon page, there are tiers that they like tiers, right? So you can pledge at this level or that level. All of the levels get you the same rewards in my system. I'm not doing any sort of complicated system where you get more and more goodies for more and more money, because this is a bare bones operation that I'm doing in my spare time here. The amount of appreciation goes higher and higher the more money that comes in, but you'll get the AMAs and you'll get the feeling of satisfaction. The other thing to announce is that today we have a special show in that there are no guests. This is a solo show, just me talking. The topic is a big one. Why does the universe exist? Why is there something rather than nothing? Why is there anything at all? I will give you an answer. I will talk about various different answers. This is not the kind of question that is really straightforward to definitively answer in a way that everyone agrees, but I'll try to sketch out some of the possibilities. It's obviously a big question, the very biggest questions. That's why we're here at the Mindscape podcast. So let's go. I'm often asked when I first got interested in science or in physics or cosmology. Different people come into a field like this in different ways. Some people don't discover it till rather late. They're in college or something like that. Other people discover it rather early. I was in the very early camp. I was a kid. I say that I was 10 years old. What I actually remember was that it was in fourth grade when and my classmates and so forth started talking about science in a more directed way, not just whatever was going on in class that day, but I really became fascinated by it. I know a lot of people became interested because of science fiction, because of movies and TV and books and whatever. For me, it was actually nonfiction books. I would just read books in the local public library, which I haunted for many, many hours. And I would read books on quarks and the Big Bang and general relativity and particle physics, quantum mechanics. And I said, I want to do this. This is what I want to do for a living. And, it makes you think, right? You start thinking about these great ideas you've never been exposed to before. And I could usually, think my way through and maybe not understand things perfectly, but at least, come to some comfort level with the various words and ideas that were being batted around. The one that always sort of stuck me a little bit was, why is the universe here at all? When I would fall asleep at night, thinking about something that I had read in a cosmology book or whatever, at some point my brain would come on to this question of, what if I weren't even here? What if the universe was not here? What then? And then that was it. No more sleep for me that night. That was the kind of thing that kept me up at night. That and Bigfoot, but that's a whole nother story. So this is a famous problem, right? Why does the universe exist? Why is there something rather than nothing is a famous way of putting it. I'm not really an expert. I'm not sure what it means to be an expert on this question. I guess I'm more expert than the average person. Certainly on the physics side of things, I am pretty well aware of the relevant issues, and I enjoy talking about, reading about, learning about the philosophical side of things and even the theological, religious side of things. So I was invited to write an article, write a paper about this, a review paper, invited by Eleanor Knox and Alistair Wilson, who are two philosophers of science, to an upcoming volume called The Routledge Companion to the Philosophy of Physics. And foolishly, I said yes, although it was a lot of fun after the fact. Your memories don't always correctly reflect how you were feeling at the time. While I was writing it, it was a tremendous hassle, but now that I've written it, I remember it as great fun. So you can find the paper online on my website or elsewhere. It's simply called Why Is There Something Rather Than Nothing? And I thought that would be a good topic to dive into for my first ever solo podcast for a number of different reasons. I mean, the biggest reason being that it's sort of a representative topic for the kinds of things that I want to talk about as the podcast goes forward. It absolutely requires that we take seriously the union and certainly the intersection of physics, but also philosophy and, as I said, religion, because one of the answers that's going to be given for why their universe exists is that because God made the universe, right? That's going to be a popular answer. I can't deny that. So you have to think about that. Is that the right answer? What is the evidence, one way or the other? Does it hold up? Is it the best way of thinking about things? So that's what we're going to do. I'm not the first one to talk about this, of course. In fact, in very recent years, it's the kind of topic that pops up. If you go and Google, why is there something rather than nothing? Why does the universe exist? You'll get plenty of hits. And I think that there's been a misimpression that a lot of people have gotten. So part of the purpose of this particular discussion will be to correct some misimpressions. The misimpression I'm referring to is the idea that advances in modern physics have answered the question, why does the universe exist? Answered it in a way that hadn't been answered before. And I think that's just wrong. I think that is not true. Advances in modern physics have shed light on what it means to ask the question. They have given us new ways of thinking about what would qualify as an answer, but they have not told us what the answer is. In particular, there's a little motto that goes around saying the reason why there's something rather than nothing is because nothing is unstable. And this has something to do with the quantum vacuum state. So I'm here to tell you that does not answer this question that we're interested in. The motto, nothing is unstable, was invented by Frank Wilczek, Nobel Prize-winning physicist. And he wasn't really referring to the question of why there's a universe at all. He was referring to the question of why there is matter in the universe, in particular, why there is more matter than antimatter. And you can try to explain that. We don't know what the right answer to that question is, but you can try to explain it in terms of the instability of certain quantum states. That's a perfectly sensible thing to do. But why there are quantum states, why there's a universe at all, why there's space-time is completely unrelated to this particular thought that was in Frank Wilczek's mind. So, he's a brilliant guy. He understood this perfectly. He knows what he's talking about. But in boiling it down to a motto, I think that its applicability got a little lost. So that's not the answer. In fact, I think if there is any answer to the question of why is there something rather than nothing, the answer is there isn't an answer. The answer is that the issue of the existence of the universe is not the kind of thing to which we can attach why questions and why answers. This is why, of course, it becomes a little bit of philosophy that we talk about, well, what do you mean by why? What do you mean by something and nothing? And this kind of discussion might very well be frustrating or boring to you. I get that. No problems with that. I'm sympathetic. This discussion is largely not going to be for you if you're not that interested in a very careful, rigorous parsing of the meaning of these questions and how they could possibly be applicable. That's the work we have to do to try to understand what the possible answers could be to why there's something rather than nothing. So that's the plan for this discussion. I'm going to talk about what it means to ask why something is true, why something is the case. Then we're going to talk about what it means for there to be something rather than nothing. And then we can talk about some of the more down-to-earth physics concerns, some of the ideas that we do have. After all, the universe obeys the laws of physics. So what the laws of physics are and how they apply to the universe are certainly going to be relevant when you talk about why there's something rather than nothing, even if they don't provide a once-and-for-all answer. Okay, so that's the background. With that background in mind, we can think about the question. It's the kind of question that is so big and obvious, right? Why is there a universe at all? Why does reality exist? You might have thought this was hotly debated 2,500 years ago, that, in the Athenian flowering of science and philosophy, Plato and Aristotle probably bandied about this question and offered, colorful dialogues or extensive treatises about it. But no, actually, as far as I can tell, this was just not a question they chose to address. They had different opinions about how the universe came to be. Plato had his idea of the demiurge and so forth. Aristotle invented his idea of the unmoved mover, which is basically God. But the issue of maybe the universe couldn't have existed or might not have existed was not really a hot topic back then. It wasn't until Leibniz in the 18th century, Gottfried Wilhelm Leibniz, one of the co-discoverers of calculus along with Isaac Newton. Leibniz was a very influential philosopher and physicist, even though the word physicist wasn't that popular back in the day. It was Leibniz who first posed the question in the modern form, why is there something rather than nothing? It was later dubbed the primordial existential question. And it's a good one. We can ask it anyway. We can't demand that there is a satisfactory answer. This is going to be part of my sales pitch here. It's perfectly good to ask questions like this. But when you are dealing at the very boundaries of knowledge, the things that we don't have familiarity with in our everyday lives, what you can't do is simply insist before you even dig into the question that it's going to be the kind of thing that's going to give you the kind of answer you're used to. I mean, why would it? It's a very different kind of question than we're ordinarily faced with in our day-to-day lives. Leibniz in particular had a slightly hidden agenda. It wasn't very hidden. It was an open agenda. He was trying to develop an idea that he had called the principle of sufficient reason. The principle of sufficient reason is basically the bumper sticker that you can get that says, everything happens for a reason. Basically, he says that anything that occurs in the world does so for a good reason. There's a reason why. Now, this is one of those things that seems reasonable, right? When we see things happen, they don't just randomly happen. There seems to be a pattern and orderliness to nature. So things happen for reasons why. And Leibniz says this is a rule. He says, in other words, it's not just something we happen to notice, that things happen for reasons. It's something that will always be true, an absolute foundational principle of how reality works. And if you say that, then of course, the existence of the universe is something that has a reason. The universe happens, it exists. So Leibniz says clearly there's a reason why the universe happens. So Leibniz, in his philosophy, was, I know what the reason why is. It's God. God created the universe. That's a very simple answer. Now, as very clever, sophisticated, highly educated 21st century thinkers, I'm sure you're sitting there thinking, but wait a minute. What is the reason that God exists? Isn't there a worry of an infinite regress here? And Leibniz, he's thought of this. He's way ahead of you. He says, no. God is his own reason. That's the unique thing about God. Unlike the universe, which may or may not have existed, God necessarily exists. So God is the one thing that doesn't need an external reason. Doesn't need a reason other than himself. God is his own reason for existing, and he's the reason for everything else existing. So if you can buy that, if you can buy into this framework, it is at least consistent, right? It's at least self-contained. It does provide answers to the questions that we've been posed. It's not necessarily been a very popular idea since then. It depends on your attitude towards other questions. Roughly speaking, if you're religious, this sounds like a good strategy. Everything needs a reason. The universe's reason is God. God's reason is his own self. People like David Hume scoffed at the idea later on. The famous Scottish philosopher David Hume, who is one of my intellectual mentors in some sense. David Hume is someone I didn't think that much of when I first encountered him in college. But then again, I went to a Catholic university and we studied the parts of David Hume that were less interesting. And now I realize in my old age that Hume is right about a lot of things. You can learn a lot by reading David Hume. And Hume just says, look, I don't see any reason why there should be a necessary being. How do you know that something like God is a necessary thing? And Hume pointed out, he didn't spend a lot of time on it, but his basic argument, which I think is correct, is, look, all of your arguments in favor of the idea that God is a necessary being basically are circular. They basically come down to the idea that you insist that everything has a reason, that nothing can just be. If you don't insist on that, then the universe can just be. And if you do insist on that, then you're cooking the books. If you insist that everything has a reason, then yes, you get to this result, but maybe some things don't happen for reasons. Maybe there aren't necessary beings. And this has been, a widely accepted point of view among at least many philosophers and thinkers ever since then. Bertrand Russell, the 20th century philosopher, put it very straightforwardly. He said, I think the universe is just there, and that's all. It's a brute fact. That's all there really is to it. And basically that's the position I'm going to defend myself, but I should note that there is sort of a middle ground. On one extreme there is a definite, definable, point-at-able reason for the universe existing. It's God or something else. And on the other side of the spectrum, you have, it just is. Stop asking questions. In between, you have, well, the universe didn't have to exist in this particular way, but there is something nice about the universe as it is. There's something special, maybe more elegant, beautiful, better in this way of the universe existing than not existing. Of course, then you reach that question, why should the universe obey that principle of elegance or simplicity or whatever it is? But, maybe that's a brute fact. It's a slight shift of where the brute facts are from the existence of the universe to the thing that the universe satisfies, the kind of criterion that it enables. So that's the history in a nutshell, very, very quickly. There's a lot of people talking about this. You see them talk about it more and more when the 20th century comes along, and opinions differ. You will not be surprised to learn. Not everyone agrees. So let's, given that history, lay some of the groundwork, be a little bit more careful about what we mean by why something might exist. In other words, what we're asking is, what do you mean when you ask why something is the case? What is the kind of answer that would possibly satisfy you, right? And this is a hard question. We've all had, or at least we've witnessed, the experience of a little kid asking some why questions. Why is the sky blue? And someone says, well, the light from the sun is reflected differently, whether it's blue or red. And the kid says, well, why is the light deflected differently? And you say, well, it's because of the molecular structure of the molecules in the air and how they interact with light. Guess what? The kid can say, well, why is the molecular structure that way? And you could talk about Schrodinger's equation if you wanted to. But usually you just say, stop asking these questions. It just is that way, okay? So I'm going to call this the little kid problem. Given any answer to the question, why are things one way, you can always ask, well, why is that true? Why is that the case? This is what Leibniz was trying to wriggle around by saying that God is the end. The buck stops at God. He's necessary. You're not allowed to ask why he exists. He exists for his own reason. But if you don't have that option to go to, then you can just always keep asking more and more questions. In the paper, I called this the problem of explanatory regression. Why is this true? Because of something. Why is that true? Because of something else. And it goes potentially infinitely far. Sometimes people like Aristotle said, we can't have an infinite chain of causes why things are true. I'm not sure why that's right. I'm not sure why you couldn't have an infinite chain, but we're not going to dig into those particular debates right now. So that's a problem, that when you have an answer to a why question, there might always be another why question that pops up. But putting aside that problem, let's just look at the individual answers. So let's bring it down to earth. Forget about the universe. Let's say that the doorbell rings. You open the door and there's someone there carrying a pizza. So you ask your partner, why is there a person here carrying a pizza at our door? That's a typical why question that you might be confronted with in your everyday life. And if you think about it, there could be many, many answers to that. There's sort of an obvious answer. Oh, because I ordered a pizza, right? That's a possible answer. Or you could be a little bit more specific, because I called in a certain way on the phone, the pizza place, or because I went on the internet. But what about things like because I was hungry? What about things like because we live in a capitalist system where I'm allowed to exchange money for goods and services? What about things like because space-time is four-dimensional? I mean, if space-time were not four-dimensional, maybe there wouldn't be any such thing as pizza, and it wouldn't have arrived, right? Maybe because gravity is attractive, because if gravity were repulsive, we wouldn't have planets, and therefore we wouldn't be able to deliver pizzas. If you're this kind of annoying stickler about what the why questions might be, which, by the way, is professionally called a philosopher, if you're that kind of person, then you see there's a multiplicity of possible answers to a simple question like, why is there someone at the door carrying a pizza? And of course, Aristotle knew this way back in the day. So Aristotle famously distinguished between different kinds of reasons why different things happen, different kinds of causes, they're usually called. And I don't want to go into that. We're not here to debate Aristotle or anything like that. But for the purposes of our discussion about why the universe exists, it is nevertheless useful to distinguish between two different possible kinds of answers. One kind of answer would be the mechanism that might bring something into existence, right? In the case of the universe in particular, you might have a physics theory that explains why the universe came to be through the workings out of some laws of physics. That would be a mechanism that brings the universe into existence. As opposed to that, or at least next to that, there is the reason why that particular mechanism worked at all. Right? If you have a mechanism that explains the Big Bang, why the universe came into existence, well, why is that mechanism right? This is the more traditional, I think, sense of why the universe came into existence. So these roughly correspond, this idea of a mechanism and a reason, correspond roughly to what Aristotle called the efficient cause and the final cause. There are details that are different, which is why I'm not getting into Aristotle. But I think that for the purposes of the discussion, it is important to discuss both the mechanisms that could have brought the universe into existence, if any, and the reasons why that might have happened in the particular way that it did. You'll not be surprised to hear that talking about mechanisms is relatively straightforward. That's a physics problem, right? What happened at the Big Bang, before the Big Bang? Are there more than one Big Bangs? These are not easy questions, but they lie squarely within the realm of what we know and love as physics, as cosmology. We know how to talk about these. There are probably equations involved in them. The idea of reasons why, the reason why this particular mechanism worked, the reason why the universe is one way rather than another, is harder. This is something that is not in the wheelhouse of what physicists do for a living. Physicists can say, gravity is attractive because of the sign of Newton's constant in the equations of motion. But if you say, okay, why? What is the reason why Newton's constant has a certain sign? They might say, well, it has to do with the stability of the vacuum state in the theory or something like that. But if you keep asking these why questions, like the little kid, eventually they'll just say, no, that's just how it is. Those are the laws of physics that we discovered. And the reason for this, the reason for the existence of reasons in this particular way, is that according to the lights of modern physics, what you and I in our everyday life know as a reason, the pizza guy came because I ordered pizza because I was hungry, that is not fundamental to how the universe works. Unlike what Leibniz had in mind, where the fundamental nature of reality is a story of things happening for particular reasons, that is not how modern physics talks about the universe. Modern physics talks about the universe in terms of laws of physics, which are patterns. You start somewhere. You start with a particular state. Here's the universe with all the stuff in it doing different things. And then I give you an equation that says, starting from this stuff, here's what's going to happen next. That's true whether it's Isaac Newton's equation of motion or Maxwell's equations or Einstein's equation or Schrodinger's equation. This is the paradigm that physics works under. And at the fundamental level, that's the answer to every why question. Why did a person carrying pizza arrive at my door? Well, because of the laws of physics and the initial conditions for the universe at the Big Bang. That's a possible answer. You could give that. Your partner will not be satisfied with that particular answer if they're demanding to know why a pizza just arrived. You can't just say, it's the laws of physics plus initial conditions at the Big Bang. You're not going to be sharing that pizza with a happy partner if that's going to be the case. The actual reasons that we know and love, that we would say in a more intuitive everyday situation, are emergent. They're not fundamental. So if you're talking about the fundamental laws of physics, you're speaking a language of patterns of this happens, then that happens, then that happens, then that happens. That's how the laws of physics work. All of the talk that we give about reasons why are at a higher level of description. I talk about this a lot in my book, The Big Picture. It's an approximation. It's a useful way of talking about the world in sort of a coarse-grained, approximate way. The human scale reality is one where a talk of reasons why makes perfect sense. I ordered the pizza because I was hungry, even though words like hungry are nowhere to be found in the fundamental laws of physics. Now, some people will argue that it can't be that way. You can't just remove reasons why from the fundamental laws of nature, because if you do, then all hell breaks loose. Then it's just chaos and anything can happen, right? You have no explanation for why one thing happens rather than another. So the distinction I'm trying to draw, it's not that anything can happen. It's not that there are no rules. It's that the rules that we call the laws of nature have a very particular form. All they do is say, if this, then that. If this is the case now, then that will be the case a moment later. They don't say why this was ever the case. They don't say why it's the case that things evolve in that way. They're just a rule for chugging along what happens in the universe as time passes. So you can ask, why are the rules that way? We don't know. That is very, very much subject to the little kid problem. Why is the universe, why are the rules one way rather than some other way? You can keep asking that why question. So my point is that the kinds of answers to questions, why is this the case? The kinds of answers that we're used to getting in our everyday context. The pizza came because I ordered it because I was hungry. Those kinds of answers might not be available to us when we're asking questions about the nature of the universe itself. Those kinds of answers are part of a toolkit that we have for our everyday lives, for the emergent level of behavior, for human scale things. We have no right to demand that the same kind of reasons, the same kind of vocabulary, has any applicability at all to questions like, why is there a universe? What happened at the Big Bang? Why are the laws of physics the way they are? There might be answers to those questions. I'm just saying we don't have the right to demand it. We have to be open-minded. Let's see what happens when we dig into what those laws are. Okay, so that's my background about what does it mean to ask for a reason why when we can and cannot actually do that. Now let's go to the question of what does it mean to say something versus nothing, right? What do you mean to ask when you ask about why does the universe exist? And here there's, again, two sort of sub-questions that we're aiming at. One is the question of, we look at the universe, we can think of the universe as there's space. Space is the arena where things happen, right? I'm here, someone else is over there, there are planets and stars up there, and there's stuff in the universe. Me, planets, stars, and so forth. And you can ask, why is there stuff, right? You could define nothingness as not an absence of the universe, but as simply empty space in some sense, right? If we had space but no stuff in it, that would be a kind of nothingness. It would be like the vacuum in some sense, right? Maybe there's a question of why there is matter in the universe. This is kind of the question that Wilczek was getting at when he said maybe nothing is unstable. That's one kind of question. The second kind is, why is there a universe at all? Why is there space itself? Forget why there's stuff in space. Why are there 3 dimensions of space? Not just versus 10 dimensions, but why are there dimensions of space at all? This is harder. The second question is probably what people have in mind when they're, Leibniz or Hume or Russell or whatever, when they say this question about why the universe exists, why there's something rather than nothing. But it's harder. And therefore, there is a common strategy among people who claim to have answered the question of why there is something rather than nothing, which is that really they're answering why there is stuff inside the universe, not why there is a universe at all. These are both interesting questions, so we can talk about them a little bit, but let's just be clear what's going on. We don't want to claim credit for answering one question when we're really addressing another one. The why is there stuff in space versus why is there space at all? So what do we mean by space, right? I mean, this is, if you're at this level of carefulness and asking these questions, some of the easiest, most obvious things that you think you're familiar with need a little bit more careful consideration to make sure we know what we're talking about. After all, there was this guy, Isaac Newton, who gave us a wonderful theory of physics called classical mechanics. I don't think he called it that. Maybe he did. I don't know. But Newtonian mechanics, it's sometimes called. One of the features of Newtonian classical mechanics is that, again, there's stuff in space evolving with time, and that space and time are both themselves absolute. There's something called space. It's absolutely agreed upon and objective. Everyone agrees on what space is. Everyone agrees on where things are, how they're moving through the universe. There was an absolute notion of where you are in the universe, in Newtonian space-time. So if you naively take Newton's paradigm, he gave us equations, right? He said, here's how gravity works, here's how inertia and forces work, and so forth. He gave us rules for saying, given some stuff scattered through space, how does it evolve with time? Time itself is absolute, just like space. So again, naively, and I keep saying naively because these are theories, right? Newtonian mechanics is a theory suggested by Newton. You might imagine ways to tweak the theory, to slightly change it, okay? So when I say naively, I mean, what is the most straightforward, direct implication at face value of a theory like this? Not that it is an absolute necessary part of that theory. Anyway, naively, Newton's theory implies the universe is eternal. Space and time just are. They exist. Time extends from past infinity to future infinity. There's nothing in Newton's equations that says the universe has to begin or end. There's stuff moving in the universe, and that will just keep moving forever and ever. That's the straightforward reading of Newton's equation. Now, Newton himself, I'm not sure if he did believe that or not. I don't know whether I know that he thought that God was responsible for the universe. I know that Newton was very religious in this sense, and he was very happy to talk about how God had something to do with the universe, not just bringing it into being. I mean, part of what he said was that, the beauty of classical mechanics, of this framework he invented, it was so beautiful, it had to be God's design. But he also believed that maybe it wasn't quite beautiful enough. He was smart enough to know the kinds of questions he was interested in were planets moving in the solar system, right? Explaining the motion of the planets in the sky. And he was smart enough to know that in his theory, unlike his predecessors, Kepler and Copernicus and so forth, not only did the planets move in the gravitational field of the sun, but the planets had their own gravitational fields. So they would influence each other. So they wouldn't simply orbit the sun forever. They would nudge each other off of their orbits. Ultimately, the solar system should be unstable. So Newton actually thought that God would occasionally come in and clean things up, that he would fix the orbits of the planets to keep them going for however long that was necessary. Again, that was part of his thought that was not popular later on. Pierre-Simon Laplace, circa the year 1800, was very definite that he thinks that the universe can be explained without an interventionist God, that the universe can simply obey the rules of classical Newtonian mechanics. These rules, by the way, don't change that much for our present purposes when it comes to 1905, when Albert Einstein puts the final finishing touches on the special theory of relativity. You may have heard that special relativity says that space and time are not absolute anymore. They are part of one four-dimensional thing called space-time. And that's true, but in special relativity, space-time is absolute. So you might not agree on where you are in space, but everyone agrees on where they are in space-time. And furthermore, that space-time is just a background. It's there, we all live in it. And again, straightforwardly, if you obey the equations, space-time exists forever. It goes from the past infinity to future infinity. So special relativity doesn't really change the question, why is there something rather than nothing? In either special relativity or classical Newtonian mechanics, there's just a posit that here you go, this is space or space-time, and there's stuff in it, and it's going. There was really no explanatory apparatus that you could reach for within the theory itself. That did change 10 years after special relativity when Einstein put the finishing touches on general relativity. In the general theory of relativity, now space-time is still very important. The difference is that space-time is now dynamical. In general relativity, space-time is not a mute, fixed, unchanging background on which everything else happens. Space-time is a player in the game. The force of gravity, in the general relativistic way of looking at things, is a manifestation of the curvature of space-time. So when you have matter and energy, that forces space-time to curve. When you have curved space-time, that pushes around the matter and energy in what you and I know as the law of gravity. When an apple falls from a tree, Einstein would say that's because the Earth is curving the space-time in the vicinity of the apple tree. So that's a little bit of an important change for our present purposes, right? In general relativity, space-time is not this separate thing. It's not just the stage on which the drama is being played out. It's an actor in the drama itself. And it didn't take too long. In the 1920s, people realized that the universe is expanding, right? Edwin Hubble and his collaborators showed that not only are galaxies moving away from us, which everyone knew, Hubble measured the distances to these galaxies and discovered that galaxies that are further away are moving away from us faster. In other words, the universe as a whole is getting bigger. And everyone instantly realized if you wind the clock backwards, if things are moving away toward the future, they were closer in the past. And there was a solution to Einstein's equation that said, you know what, everything is just going to hit. Sometime in the past, some number of years, everything in the universe is on top of everything else. Georges Lemaitre, a Belgian priest who was one of the founders of this idea, called it the primeval atom. And today we call it the Big Bang. That moment, which we now know was about 14 billion years ago, when everything that we know about in the observable universe was in the same place. According to the equations of general relativity, the Big Bang is a beginning. If you trace what happens backward in time, unlike in Newtonian mechanics or special relativity, in general relativity, there's a singularity past which you can no longer push the equations. It is no longer true in general relativity that just because we're here now and there's stuff in the universe and it's moving around, that stuff was always here. There can be a moment in time when the universe comes into existence. And the Pope at the time said, this is brilliant. This is just what God said in the Bible. And he asked Lemaitre to sort of justify the creation story in Genesis using these new cosmological discoveries. And Lemaitre said, no, that is a very bad idea. What if tomorrow someone invents a new theory where the Big Bang was not the beginning of everything? Then we'll be in trouble. So he knew better than to do that. Whether or not you have a religious implication of it, circa 1920s, the story seemed to be the universe had a finite age. There's only a finite number of years between the beginning of the universe and now. And now we know that number is about 14 billion years. What we don't know is whether or not that was the beginning. because it's an implication of general relativity under the right assumptions, but general relativity might not be right. General relativity doesn't include quantum mechanics. We need a quantum theory of gravity. Maybe there are extra dimensions of space. Maybe there are multidimensional brains moving in some string theory construction. Many people, including myself, by the way, have proposed scenarios where the Big Bang is the beginning of our local observable region of the universe, but it's not the beginning of the universe as a whole. So we don't know is the answer to the question, did the universe have a beginning in general relativity? Maybe the Big Bang was the beginning. We'll talk about this in a little bit more detail later. There is a theorem that is sometimes bandied about, the Bourdais-Guth-Vilenkin theorem. These are my friends, Arvin Bourdais, Alan Guth, Alex Vilenkin, some cosmologists in the northeastern United States. And they were interested in the question of, can inflation go on forever? Inflation is a theory wherein in the very, very early universe, there was a tiny moment of time when the universe underwent a hyper-fast period of accelerated expansion. So just like we discovered that our universe is doing today, back then there was this dark energy, essentially, that was incredibly dense, incredibly powerful, pushing the universe apart, causing this thing called inflation, and then inflation would end. That dark energy would convert into ordinary matter and energy, and you and I would see that as the hot Big Bang that we know and love. That's inflationary cosmology. What Guth and Vilenkin and some other people worked out is that inflation can end in some regions of the universe, but it doesn't have to end everywhere. It can end here, but it can keep going other places. So they invented what is called eternal inflation. Even if inflation ended for us, somewhere else it's still going on, even today. And they asked the question, could this be also true in the past? Eternal inflation is eternal toward the future. Was it also eternal toward the past? So they wrote down and proved a theorem that said that according to the rules of classical spacetime, whether or not Einstein was right about how classical spacetime behaves, as long as you believe in the existence of classical spacetime, inflation cannot be eternal to the past. So there had to be a singularity back there rather than just an eternally inflating universe. Now, if you Google the Bourdais-Guth-Vilenkin theorem, the large majority of references to it are not from cosmologists or other physicists. They are in theological contexts because people are taking this as a theorem, a proof that the universe had a beginning. That is completely wrong. The Bourdais-Guth-Vilenkin theorem does not prove the universe had a beginning. It just proves that inflation was not eternal toward the past. It is completely compatible with the theorem that the universe bounced at some point in the past, that we live in a baby universe that came out of something else, that we live in a cyclic universe that bounces over and over again. There's many different possibilities, all of which are eternal and completely compatible with the Bourdais-Guth-Vilenkin theorem. So we don't know is the answer to the question, did the universe come into existence? If it did, then you'd be forgiven for thinking that's a good reason to think something started it, right? If the universe started, something started it is a very natural way of thinking. It might not be true, but it's a natural place to go in your thinking. But if it lasted forever, then that's a less tempting place to go. Honestly, we don't know which one is true. The other thing, of course, is that the Bourdais-Guth-Vilenkin theorem refers to classical spacetime, right? That is to say, even if there are quantum mechanical particles in the universe, we treat the universe itself, the space-time in which we live, the space-time that obeys the rules of general relativity, as classical, as something that's definitely there. There's no uncertainty principle. There's no superpositions or anything like that. We know, most of us accept the obviously true fact that that's not right. That ultimately space-time itself is going to be quantum mechanical just like everything else. So what do we say when we have to combine quantum mechanics with curved space-time? The answer there is that we don't know. Sorry to be telling you things that we don't know, but this is what life is like on the cutting edge of theoretical physics and cosmology. Sometimes we have to be honest that we don't know the answer to things. So quantum gravity is something we don't have the answer to. In fact, if you're really honest about it, quantum mechanics is something that we don't really have the answer to. Quantum mechanics came along in its final form in the 1920s, and it's a very, very good theory for predicting the results of experiments. As I'm sure you've heard, quantum mechanics says that when you predict the results of experiments, you get a probability, not something definite. You say, well, there's a 50-50 chance the spin will be clockwise or counterclockwise or something like that. That's very good. We can predict all these experiments. We can use it for technology. We can predict the existence of the Higgs boson. We can go and find it. We can build lasers and transistors and so forth, all based on the predictions of quantum mechanics. What we don't have is an understanding of what quantum mechanics really says. This is the topic of a book I'm working on right now called Something Deeply Hidden, which should be out in fall of 2019. And I'm sure as time goes on, we'll be returning to the question of quantum mechanics here on Mindscape over and over again. It's a fascinating topic intrinsically and certainly to me. But what I mean when I say we don't understand it is we can give predictions for certain very particular situations that will pop up in an experimental laboratory, but we can't tell you what is actually going on. So we can say, when I look at an electron that is spinning and I measure its spin, I'll measure it to be spinning clockwise or counterclockwise with a certain probability. But if someone says, well, what do you mean by measure? What exactly happens when you measure it? Is it really evolving differently depending on whether I measure it or not? These are questions we don't know the answer to. Not because we don't have answers, but because we don't agree on what the answers are. As I'm sure I will discuss in later podcasts, I'm a proponent of the Everett or many worlds version of quantum mechanics, which is a terrible name for marketing purposes. I like the name for descriptive purposes, but really it should just be called pure quantum mechanics. The many worlds approach says that there is a quantum wave function and there is nothing else. And there's a Schrödinger equation, and there is nothing else. It's the simplest, most stripped-down version of quantum mechanics. Now, I'm not going to pitch Everett and many worlds quantum mechanics to you right here, but I'm mentioning it because as soon as you start talking about things like stuff popping into existence out of nothing or the quantum vacuum being unstable, you have to have an idea about what quantum mechanics is, right? You can no longer be agnostic about these important foundational questions. So when I talk about quantum mechanics over the course of the next few minutes, it will be implicitly in this Everettian point of view, but hopefully that doesn't matter too much for anything that we say. The point is that in quantum mechanics, we describe stuff not by particles with positions and velocities, but by what's called the wave function. The wave function in quantum mechanics is basically, effectively, we use it as a tool to calculate the probability of getting various different outcomes. When you look for the location of an electron, where is it going to be? You use the wave function to calculate the probability. Some people will say that's all it is, just a tool for calculating probabilities. A good Everettian will say, no, the wave function is an exact representation of reality itself. That's what reality is. It's a wave function. Fine, we don't need to debate that right now. The point is, a wave function of what? So when quantum mechanics first came along, people were interested in electrons orbiting in atoms. So you would have a wave function for an electron. You would have the very first version of this formalism that was written down by Schrödinger. Erwin Schrödinger wrote down the famous Schrödinger equation, and he was just dealing with one electron moving around the nucleus of an atom. And there you can ask the question, going back to our actual topic here, can things appear out of nothing? Is there a reason why things happen? In the non-relativistic original baby Schrödinger equation, you're just describing one electron moving in some force field of electromagnetism, and electrons never come and go. In that version of quantum mechanics, that simple down-to-earth version, there is one electron. If you observe it, you will see it somewhere, and that's the whole story. There is no special help given to us in this question of why the universe exists. However, we know better than that, of course. There's more than one particle in the universe. For example, there are fields in the universe. There's the electromagnetic field, there's the gravitational field, and so forth. Eventually, physicists realized that what we thought were particles, like electrons, neutrinos, quarks, and so forth, everything you and I know and love as a particle is actually a vibration in some sort of quantum mechanical field. So not only is there an electric field and a magnetic field, which when they vibrate give us photons when you observe them, there is a neutrino field, which when it vibrates, we see a neutrino. When there's an electron field, and when it vibrates, there's an electron, and so forth. So the modern best theory of the universe is called quantum field theory. Quantum field theory describes the universe as a bunch of gently jiggling fields filling all of space, surrounding you. You yourself are an interacting bundle of gently vibrating quantum fields. I hope that makes you feel good about yourself. The great thing about quantum field theory is that it can describe not only the existence of particles as we observe them, but the creation and destruction of particles. You can make particles. When we discover the Higgs boson at the Large Hadron Collider, you don't actually see the Higgs itself. It decays too quickly. It changes into other particles, and we see those decay products. That's what can be described by the formalism of quantum field theory, how particles change into each other, or even how particles are just created out of supposedly nothingness. So you see how all this digression is coming back into our topic that we're talking about here. In the framework of quantum field theory, you can very easily imagine evolution according to the laws of physics that starts with empty space where if you lived there, you would look around and not see any particles, and in the ordinary evolution of things, particles would come to be. This is what Frank Wilczek had in mind when he said maybe nothing is unstable. It all comes down to, it's not that anything can happen. If you were in empty space, you don't need to worry that suddenly particles are going to pop into existence. They happen under the right circumstances. So the subtlety here is the definition of the phrase empty space. When physicists talk about empty space, usually what they mean is the vacuum of a quantum mechanical theory, and that's not a machine that cleans up your room. The vacuum is just empty space. In particular, it is the lowest energy state in a quantum field theory. If you imagine you have empty space, that has some energy, maybe zero, or depending on how you define things. If you add a particle to it to construct a different state, now it has more energy, right? So vacuum, the technical definition of empty space, is the state of lowest energy, the thing where there's nothing going on. But interestingly, there can be temporary lowest energy states. In other words, you can have a state that looks like it's the lowest energy state, but secretly it can evolve. These are called false vacuum states. This is what would drive that period of inflation that we talked about. If there were a state of false vacuum that could make the universe accelerate and then suddenly all of its energy got converted to particles, you would see particles coming into existence where there hadn't been any particles before. That is certainly coming close to what we have in mind when we're asking this question: why is there stuff in the universe, then not stuff? So all of this leads up to me saying that may very well be true. So if what you care about is why is there stuff in the universe, then the answer might very well be found in the laws of physics as we understand them now, in quantum field theory, in the cosmological applications to quantum field theory. That's the kind of question we can answer. However, you might be more ambitious than that. You might want to know not just why do particles come into existence out of empty space. You might want to say, why does empty space come into existence? And here's where we get a little bit more wild. So let's take a breath, congratulate ourselves on coming to some understanding of why there might be matter in the universe, but now start talking about why there's the universe itself. So the question in front of us is, can the universe simply be all by itself, even if the universe has a beginning? So again, we've been a little bit agnostic about whether or not the Big Bang really is the beginning of the universe, but we can still ask the question, whether or not the universe had a beginning, does it need a cause? Does the universe need something outside to bring it into existence? So the physics here is that there are two very different possibilities for the universe on its largest scale description, according to the rules of quantum mechanics. Of course, it's always possible that quantum mechanics itself is wrong. Every theory of physics has a chance of being wrong. We should be open-minded about that. But if quantum mechanics is wrong, then we have no clue what's going on. The current state of physics is that there's zero evidence that quantum mechanics is wrong in any way. So let's go with quantum mechanics as our theory. So Schrödinger's equation is the equation we use to describe a system according to the rules of quantum mechanics. And it works for literally any quantum mechanical system. There are different versions of Schrödinger's equation for electrons, for quantum fields, for the universe itself. And what Schrödinger's equation is basically the quantum replacement for Isaac Newton's equation that say F equals ma, right? Force is mass times acceleration. You push something, it accelerates in a certain way. The thing that Schrodinger's equation does is it says, you give it a quantum mechanical system, here's how it's going to evolve. And the question is, the relevant question for our present purposes about the existence of the universe is, what is the energy of the universe? This might not be what you thought you were being asked, but this is what is actually very relevant. Schrodinger's equation acts very differently depending on whether the energy of the universe is zero or non-zero. And you might think, well, that's easy. I've been in the universe. I've seen some things that carry energy, so I'm pretty sure the energy of the universe is not zero. That's a little bit too quick. Of course, since we're doing the whole universe, it's not just the stuff in the universe that matters, but also space-time itself, the curvature of space-time according to Einstein's general relativity. And that counts when we count up the energy of the universe. And it's very plausible, it's not 100% sure, but in certain very, very plausible versions of cosmological physics, the energy of the universe is exactly zero. If the universe is closed, for example, if the spatial topology of the universe is like a sphere or a torus or something like that, if the universe is finite in extent, then the straightforward application of what we know about general relativity seems to imply that the energy of the universe is exactly zero. We don't know if that's right, by the way. It's very easy for that straightforward marriage of general relativity and quantum mechanics to not be right. It's very possible the universe is not closed. So there are two possibilities that are very much on the table, a universe with energy and a universe without. And they have very different implications for the question of where the universe came from. If the universe has energy that is not zero, and quantum mechanics is right, so Schrodinger's equation is right, then it follows directly that the universe has lasted forever. There's something called the quantum eternity theorem. I named it that. Nobody else calls it that. But just like Newton's equations, Schrodinger's equation just says the universe continues forever, both from minus infinity in the past to plus infinity in the future. If, on the other hand, the energy of the universe is exactly zero, then there's a puzzling thing that happens where there's no such thing as time. That's a problematic thing when you're trying to understand whether the universe came to existence, if there's actually no time itself. So what Schrodinger's equation says is how the universe evolves as time passes. And what it says about a universe with zero energy is that such a universe doesn't evolve. It doesn't change. It's stationary. Now, again, you might look around and say, like, well, I've been in the universe and I've seen things changing, therefore that can't be right. But again, you need to be a little bit more clever than that. People who have studied this version of the Schrödinger equation, which is sometimes called the Wheeler-DeWitt equation, after two famous physicists who studied it in the context of cosmology, a universe with zero energy and therefore no obvious time evolution can actually have sort of hidden time evolution. Just like reasons why things happen are emergent in our macroscopic world, time evolution can also be emergent in our macroscopic world. The point is you should think about what you mean when you say that time is evolving. Something is happening and you look at a clock and the clock says, oh, it's a certain time and this is what's going on in the universe. And then, the clock says it's a different time, something else, and something else is going on in the universe. And this happens on, an infinite number of times. That's what we mean by time evolution. Down at the level of what we actually see, time evolution is a correlation between some numbers read out on clocks and some configuration of stuff in the universe. So in quantum mechanics, things can exist in superpositions. Like that electron that we were looking at, it can exist in a superposition of spinning clockwise and spinning counterclockwise. So imagine the whole universe, a whole bunch of stuff scattered throughout space in some configuration, and a bunch of clocks reading out a bunch of different times. That's one configuration of the universe. There's another configuration where, stuff is somewhere else and the clocks read different things. And another configuration where the stuff is in yet a different place and the clocks read yet different things. And in quantum mechanics, the universe, the reality of it all, is not any one of those, but perhaps it could be a superposition of all of them. So rather than, in this point of view, the universe being described as something changing through time, the universe could be a superposition of all individual moments of time in the same description. It's very tempting to say all at once or at the same time. So try to avoid those temptations because you're using temporally laden language where it's not actually applicable. So the universe could be all moments at once. The universe could be everything that might happen in a single unified description. And if that's the case, then there's no implication that the universe lasted forever. If the moments of time that are read out by a clock are emergent, are good approximations in a certain regime where we can talk about them, then the number of such moments of time might be finite. That's the thing we would expect to be true if the Big Bang really were the beginning of the universe. If time has a beginning in the straightforward sense, it's easier to accommodate that in quantum mechanics. If the universe has zero energy, time is emergent anyway. Then you can have a first moment of time. Now, in either case, we have two cases on the table. One is the universe has energy and it lasts forever. The other is the universe has no energy and it's finite in time. Time is emergent. In neither one of these cases, this is the punchline, pay attention, neither one of these cases is there any implication that there needs to be something outside the universe that brings it into existence. In both cases, a universe that lasts forever or a universe that has a beginning, a finite moment of time, the description of what is happening in the universe is completely self-contained. It's laws of physics being obeyed by everything all the time. So even though that's sort of easier to see, as I alluded to earlier, it's sort of easier to see in the eternal case where things have always existed. There's not this implication that they sort of were created at any one moment. In the case where time itself has a beginning, that's where you have this temptation to say if there's a beginning, there's a creation, and therefore there must be a creator. There must be something outside. Or to put it a little bit more colorfully, you say, look, if you're telling me the universe popped into existence at some moment of time, you got to tell me why it popped into existence. Things just don't pop into existence. And the answer is, you shouldn't say the words popped into existence. That's not the right way of talking about it. When you say the words popped into existence, you're already assuming that time exists, right? You're assuming there's a moment when there was no universe, and then suddenly there's a moment when there's not. In the scenario where the universe has a beginning, where the Big Bang is the start, there is no moment before the Big Bang. The Big Bang was just the first moment. It didn't pop into existence. It's just that if you think about it from now going backwards rather than before the universe going forwards, if you start from now and go backwards, you hit an end, and that's it. And it makes sense in retrospect that this can happen in the case where the universe has zero energy. Remember, energy is conserved in some sense. What that means is the amount of energy in the universe is the same at every moment of time. So if you're in a universe that has energy, then in some sense that universe has to exist forever. There's nowhere for the energy to go. If there's one moment that describes a universe with energy in it, there has to be both a succeeding moment immediately afterward and a preceding moment immediately before. If the universe has zero energy, then time can end. Then there can be a moment, and there's no creation of anything because the total energy of the universe is zero. Nothing came into existence that always had been there before. So we don't need a creator for the universe according to the laws of physics. Now you might want to go deeper, right? You might say, well, I'm not about the laws of physics, man. I'm about deep metaphysical principles. And my deep metaphysical principles include something like the principle of sufficient reason, that everything that happens needs a reason. So even if you can have physics equations that describe the universe as a self-contained system, that doesn't explain the universe. And maybe, so that's a possible way to go, but it's not necessary. So let me give you very, very briefly my reasons why I don't think that's a necessary direction to go down. The point is, as we alluded to, do there need to be reasons why things happen? I tried to convince you that what we understand from physics is that we can describe the universe, even if it has a beginning or it's eternal, as in a self-contained way. We don't need anything outside. So you do need a reason why in that case. Well, usually the argument that you do need an external reason why is simply that a contingent universe, A universe that exists as a brute fact without any other explanation violates some cherished metaphysical principle, like the principle of sufficient reason. The way to get out of it is to imagine there is a necessary being. That necessary being is usually identified with God. And then God's existence, the existence of that necessary being, explains why the universe exists. So then you have to explain why we should believe in a necessary being. And again, I'm not going to go into the details here. Let me remind you, for those of you who went to Catholic universities like I did, and you heard all the different arguments for the existence of God from Aquinas and others, there's a cosmological argument, which is basically just a repetition of the idea that everything that happens needs to happen for a reason. If something is here, there needs to be a reason. If that thing exists, there needs to be a reason for that. You can't have an infinite number of reasons, therefore it ends in God. As I've tried to say before, this just begs the question of whether you actually do need reasons. If you're trying to discuss whether or not things can simply be as brute facts, then starting with the assertion, well, we all agree that everything that happens needs a reason, is not an effective counter-strategy. There's another famous/infamous version of getting to a necessary being, which is called the ontological argument, which goes back to St. Anselm and says we can conceive of a most perfect being. There's different formulations, but that's the basic idea. We can conceive of something that is absolutely perfect. And then it says, having the quality of existing is more perfect than not having the quality of existing. Therefore, if we can conceive of the most perfect being must exist. I'm probably not doing justice to this argument. It's a hilarious argument. No one has ever been convinced by this argument. Many people have believed that it's true, but they already believed in the conclusion from the start. There's many ways out of the ontological argument, of this idea that we can conceive of a most perfect being. Existence is more perfect than non-existence, therefore the being must exist necessarily. My favorite way out, which is not that popular in the philosophy community, is just to say, no, we can't conceive of a most perfect being. You think you can, but maybe you can think you can conceive of the largest prime number, but you can't because there isn't any such thing, right? Maybe you think you can conceive of a circle that we can square, a circle that we can actually geometrically manipulate into a square only using compasses and straight edges. But we can't. You can't really conceive of that because we have a theorem that no such thing exists. The point is, it's very easy to fool ourselves into thinking we can conceive of something that is just not that well defined. What do you mean by the most perfect being? Does the most perfect being hang around? Does it talk to us? Is it more perfect to talk to us than to not talk to us? Is the most perfect being male or female, or is it genderless? Is it more perfect to be genderless or to be male or female? Is the most perfect being blue, or is it colorless? What is most perfect? We haven't actually defined any of these words, which is why we think we can conceive of it, but everyone's conception might actually be different. I don't think that you can conceive of a most perfect being. I don't think it's a sensible concept. Therefore, even if you bought the fact that conceiving of it would necessarily imply its existence, I don't think you quite get there. Anyway, that's just a nod to the people who, there's really smart people who take this stuff very seriously and are convinced by arguments from the principle of sufficient reason, etc., that we need more than just a self-contained description of the universe. And they might be right, but my personal landing place here is that the universe can just be. It can just be a brute fact. So with that in mind, we still have a little bit to do, because even though that's the answer to the question, if the answer is why is there something rather than nothing, I'm on Bertrand Russell's side. I think the answer is it just is. We got to live with it. You might still ask, even if you totally agreed with me on that one, why this particular universe, right? Why does the universe exist in this way rather than in some other way? And that's often what the actual discourse back and forth about why the universe exists comes down to. People are arguing about, why does it have this number of dimensions, these particles, and so forth. Again, this is a question, why this particular universe that may or may not have an answer, right? I'm a little skeptical about a certain way of thinking that many of the world's best physicists have when they ask themselves, could the laws of physics have been otherwise? Right? Einstein himself was way smarter than I ever will be. Einstein wondered about this. Could the laws of physics have been anything else? Because I think the answer is perfectly obvious. Namely, yeah, the laws of physics could have been very different very easily. I have no trouble conceiving of all sorts of different ways the laws of physics could have been. I'm not even sure if it's sensible to say the laws of physics could not have been otherwise. Thinking of it in terms of Schrodinger's equation, as we talked about before, Schrodinger's equation says there's a certain special thing, what physicists call the Hamiltonian of the universe, which is the answer to the question, given some universe, how much energy does it have, right? That's what makes the universe go from Schrodinger's picture. And there's all sorts of different Hamiltonians we could imagine. There's all sorts of different ways we can imagine assigning different amounts of energy to stuff in the universe. So I don't even see what the possible justification would be for arguing that the laws of physics as we know them are somehow unique. I don't think that's really a starter in this argument. You could imagine that if the laws of physics were unique, that would be 90% of the way to explaining why the universe exists. There was only one way for it to exist, right? So maybe it's at least 50% of the way. It was either going to exist or not, and you had a 50-50 chance. But I think that the universe could have been very, very different than what we observe, so I'm not sure where that really comes from. It is possible that even if the laws of physics could have been different, there's nevertheless something special about the particular laws that we have. I mean, maybe the laws that underlie the universe at the most fundamental level are somehow the simplest they could be, or the most elegant or beautiful, or something like that. Now, again, they don't look very simple or elegant from our current point of view. There's nice things about them that are simple and elegant, but, there's all these particles, the top quark, who ordered that? What is that doing there? We're not very clear on why the particles have all the different masses and couplings they do. Seems to be a lot of arbitrariness in the laws of physics as we know them. But maybe that's just our view of a very messy reality that has even deeper laws that we don't know about, which are very simple and give rise to the messiness and apparent arbitrariness that we observe. That's very, very possible. I think that really all we can say there is it's an open question, right? Maybe we'll eventually find super fundamental laws of physics that are, even if they're not the only laws of physics possible or conceivable, they're the simplest or the best in some way yet to be defined. Note, that would not explain the question we're after, even if our laws of physics, our universe was the simplest or most elegant or beautiful. The little kid, who's our nemesis here, could come along and say, well, why? Why should the laws of physics be so simple? Why is that? And we wouldn't have an answer. That would just have to be a brute fact. I also can't get away without at least mentioning the idea that the local laws of physics that we observe, local I mean our entire observable universe, tens of billions of light years across, those laws of physics might be due to what is called environmental selection. We tend to think that the laws that we observe in the universe are universal by construction, but it's possible, since we only observe part of the universe, that the conditions are very, very different elsewhere. And if that's true, if conditions could be very, very different elsewhere in the unobservable universe, maybe the conditions out there just don't give rise to intelligent creatures such as ourselves. This is, of course, the anthropic principle, but really it's just environmental selection. It's the same principle that says here in the solar system, there's not some deep existential puzzle about why life arose on Earth rather than on the sun or in between the planets. There is an environment here on Earth that was just way more hospitable to life coming into existence. Maybe the universe is like that, and if that's true, we would not be at all surprised to find ourselves in the part of the universe where life can be allowed to exist. It's sort of tautologous. It's tautologous that if there are many different conditions in the universe, some of which support life and some of which don't, we will see those that support life. What is not tautologous is whether or not the universe is actually like that. We don't know whether there are different parts of the universe where conditions are very different elsewhere. We also don't know how robust life is. I mean, this is the really big puzzle, and this is maybe food for thought for a different episode of the podcast. How finely tuned are the laws of physics and conditions in our local universe for the existence of life? Some people think very finely tuned. I tend to be more skeptical, more open-minded about that because I don't know the conditions under which life could exist. There's a wonderful novel called Dragon's Egg by Robert Forward where he described life existing on the surface of a neutron star. If you think of life in very general terms as sort of a complex system interacting in an informationally dense way with its environment, that could happen under a whole bunch of conditions that I really don't know anything about. Or maybe not. Maybe the necessary laws of physics are very delicate for something like that to happen. I think this is another open question where we should be humble about what we know. We don't know the final answers here. All right. Speaking of final answers, so here's the roundup. The main points again, as James Hartle likes to say. What are the options for the real question? Not the question of why there's matter in the universe or why the laws of physics are this way rather than that way. Why does the universe exist at all? Why is there something? Why is there reality rather than not reality? So let me run through very quickly. I think there's 5 sensible things you could put forward, and I'll give you my judgments. You can give your own judgments, start your own podcast, have a little debate about it. That's good. That's why we're here. So the most obvious one is God, right? This was Leibniz's answer. Why is there something rather than nothing? Because there's a thing that doesn't need a reason. The universe is contingent. It does need a reason. There's something that doesn't, a necessary creature. That's God. That fits the role that the principle of sufficient reason laid out for it. I've told you why I don't think that's especially necessary. There's still the question of, is it a good theory, right? Does God explain, does it provide an adequate, helpful account of things that we observe around us? That is, again, a topic for a different day. Maybe that'll be a future podcast episode. But my particular answer is no. I don't think it's especially helpful. I don't think it's especially necessary. Opinions differ about that one. A second possibility is what you might call a metaverse. So kind of like a multiverse, but even bigger. And I haven't discussed this in any detail, but the point is, if the difficulty in providing reason why answers is that there's no context out of which the universe comes, right? When you provide a reason why the pizza arrived at your door, you do so within a context of things like hunger and pizzas and phones and internets and things like that, and money. For the universe, there's no outside context, right? There's no bigger picture out of which you can say, oh, here are the local reasons why. So a metaverse would be a bigger picture, maybe a multiverse, but maybe even bigger than that. So maybe a collection of many, many multiverses. And you could say, well, why our particular universe came to be in exactly the same way you would say why the pizza showed up at your house. I didn't talk about this in any detail because I see zero evidence that that's either true or necessary or helpful, but it's a logical possibility to put on the table. Third, so number 1 was God, number 2 was metaverse. Number 3 is that there's some principle that the universe satisfies, right? That the universe is the simplest, best, most elegant, prettiest, I don't know. I don't think that solves the problem. I think that, number 1, I don't see any reason that it's true. And number 2, there's still the little kid saying, well, why? Why should we be the best universe in any particular way? It would provide some satisfaction to us if that were true, right? It would scratch the explanatory itch. If you couldn't really explain why we lived in the best universe possible or most elegant, at least knowing that we did would give us some feeling that we'd accomplished something. Oh, okay, well, it's this kind of universe. That kind of makes sense. It doesn't really answer the question, but it provides some of the mental goal that we were trying to strive for when we asked the question in the first place. Again, I don't see it. I don't think it's there, but we could find it. It's absolutely possible in the future. The fourth option, which I, again, didn't mention at all in this rather long disquisition, but I think is interesting and should be talked about more, is the possibility that there wasn't an option for the universe not to exist. In other words, we've talked about the existence of a necessary being and God and so forth, but there's another way that you could sort of slice this bread. You could say, well, maybe there is simply no coherent notion of not existing. Maybe non-existence doesn't make sense in some sense. I'm not sure how to develop this idea. I'm not sure if it's right. I'm not trying to promote it. I'm not saying I believe it, but I think that, at least it deserves thinking about. And the reason why I think it deserves thinking about is when you read very brilliant people talking about this question, they often use a vocabulary that doesn't quite cohere, that doesn't quite make sense. Derek Parfit, who was one of the great contemporary philosophers who died just last year in 2017, he wrote about this question of why there's something rather than nothing very famously. And he uses phrases like, the case where nothing would have been. That's how we talk, right? I mean, what if there were nothingness? But you see what we're doing in a phrase like that, nothing would have been, or what if there were nothingness? We're attaching being to nothingness. Nothing is what was, right? Or what would have been. I'm not sure that makes sense. I don't think that the thing that exists being non-existent is a sensible thing to talk about. I think that maybe our language is fooling us here. Maybe we are fooling ourselves through our language. I don't know, but I think that philosophers should pay attention to this possibility a little bit more carefully. And finally, fifth on our list is the universe just is. If you want to know why the universe is, you're not going to get a satisfactory answer. You're not going to be happy. The universe just is. You have to accept it. You have to learn to deal with it. There's nothing further there. I like this. I mean, I don't like it sort of, in terms of, again, scratching explanatory itches, but I think it's the one that is most courageous, most brave. It faces up to the reality of it. All of these other attempts hit this little kid problem of saying, well, if that's true, why is that true? Why is that true? Why is that true? And here you're saying, nope, there is one level at which you just say that's how it is. There is nothing other than that. This is what Bertrand Russell was trying to say. I think this is probably the right answer. And I know that people don't like it, but whether we like it or not is not part of how we should judge a theory of why the universe is the way it is. So maybe the universe is special, in conclusion. Maybe there's something special about it that we're going to find or on the trail of. Also, maybe it just is. I think we have to be at least open to that possibility. What we don't get to do, whatever the right answer is, we don't get to demand that the answer take a certain form because it makes us happy. That is not what we're allowed to do as scientists, as philosophers, as theologians, as thinkers. We have to look at what the universe is doing, try to describe it and understanding the best we can. And if the answer is the universe is a brute fact, then that's what we have to learn to deal with. And with that in mind, I hope that tonight, when you go to sleep, you're not too worried about the non-existence of the universe and you can sleep well. Thanks.